to my best understanding, Amelie, from what I've read, what I've seen. There supposedly 1 point on the FRQ goes towards grading of sig figs, but just one. The catch is you don't know which question it's going to be, but in the end it's only one question, right? So on like the scoring rubric, it would say like, you know, like it has like the FRQ rubrics that you guys saw where it has like, here's the right answer, and then it kind of has like a scoring off to the side. On that side, it would say like 1 point is given towards sig figs. So supposedly that's how it's supposed to be, but the weirdest thing, I don't know if you've noticed with the 2 FRQs we've done, that's never there. Like in the past 4 years, that like has disappeared. So in like my beginning years of AP it was a thing, and now it's like, so pretty much what I say is think about them, but it should never be a thing you waste time on. Do you know what I mean? Like, so like when you get to the final answer, you normally have rounding on your brain, right? So maybe for a moment think like, how would I round for sig figs? But don't stress about it, because in the end, even if it is a point, there's plenty of other problems you can get points from. So don't stress about it. But does that help? Yeah.
Do they care about what calculator you use?
Yes, to an extent, but it's just, if it's allowed on the ACT, you're allowed to use it here. It's just like, I don't know calculators, but like the really fancy ones that like can get on the internet and stuff aren't allowed.
Yeah.
But I'd say for what I've seen, most of what you guys have should be fine. But if you remind me, maybe on Friday, I'll pull up the list just to make sure.
Okay.
So, speaking of that, someone from B7 left a calculator. But is this anybody's?
I think it was from the section.
Does that look familiar?
No, it was you and I got.
Oh, you gave it to the sub? Okay.
It looks like London's.
It looks like London's? Okay. Oh, it does look like London's, now that I think about it, because I remember looking at it. It was different.
Can
What
you
were
go
you
over
gonna
the
ask?
lab stuff? Like, the lab?
Oh, yeah. Yeah, like reviewing the different names and stuff like that. Yeah, that's a good one.
Oh yeah, that's weird.
Okay. Anything else? And we can add to it once again.
We also go over like FRQ questioning answer, like the format we should answer FRQs in.
I don't know if I can answer that myself, Izzy, but I'll put it up there and then remind me when we get to it, and we can dive into that. Okay, all right, let's jump into things. Once again, those that came in later, I'm gonna go till 11:30, but you're welcome to leave whenever you need to, or stay till the end. Okay, so starting at the top, electrochemistry. So let's do a quick review of, let's find a good marker here, an electrochemical cell. Because that's kind of what everything else is based on, is understanding how these cells work. Okay, so we're gonna draw some rough pictures here. So if I have a beaker, it is, I don't know if you've seen it so far, but they love some sort of visual with these. Not saying like you're gonna have to draw it, but understanding it and answering questions about it is like always one of the FRQs, it seems to be there. Okay, so we have our 2 beakers or 2 sides. It doesn't technically have to be a beaker, but separate components, right? There's 2 things that connects them. You need something that the electrons can flow through, right? Some sort of wire. And then what's the other thing that needs to connect them? Yeah, the salt bridge. Alright, so we learn salt bridge. Okay, so in this one, you always have 2 metals. Now keep in mind, they most often are different metals, but you actually can do one with the same metals. You can have a nickel to nickel battery if the concentrations vary, and we can talk more about concentration cells as we go. Okay, so let's say, for example's sake, which way do you want the electrons to flow? This way? Okay. So let's say the electrons are flowing this way. Now they don't have to flow that way, right? It just depends on how you set the beakers up. Okay? But let's talk through. So if the okay, pause now. In a problem, what would they give you if it wasn't told? How would you figure out which way the electrons are flowing? Yes.
If they give you it's oxidizing, reducing, or like the
Perfect, right? So if they give you the reaction, I'm gonna make one up here just to have one. We'll do our copper and silver. So So like if they give you the reaction that silver is becoming this, so it's losing electrons, that would be one way of showing, right? Now they could show you in half reactions, or they could show you in the full reaction, so it could be written like this. Turning into Cu and Eg plus. Right, so these are once again just showing you all the different ways that they could give you the same information. So they can give you half reactions, they could give you a full reaction. So how from a full reaction, how do I identify what's being oxidized and what's being reduced, Izzy?
So what's being oxidized is the ones that's adding a plus or losing its electrons. So in this case, Ag is because it has a plus above it, and
Perfect.
reducing is when it gains electrons, which is what Cu is. It's going from +2 to 0. So.
Awesome. So you have to track oxidation states. Now in this type of problem, it's a pretty easy oxidation state, but that might be something if you don't know how to do it when it gets more complicated, you might want to review those rules of assigning oxidation numbers. Okay, let's also review, it's not as common, but just in case, the notation form for a cell that they can also use where it could show this, where they do Ag a line, Ag plus, double line, Cu2 plus line, Cu. We've seen that a few times, but this is the same information as that. You read it left to right, and it's showing you what's changing. That this is becoming this is becoming this. And they always put the oxidation on the left, the reduction on the right, the double lining is like representing the salt bridge. So, okay. Final thing, so these are once again 3 different ways. They can give you a half reaction, they can give you an overall reaction, they can give you a cell notation. With the half reactions though, the one thing they could also do though is they show you both of them. But they're both, oh, I did those backwards. Hold up. Because all half reactions by formality are always written as reductions. Okay? So how do I know if I'm given 2 half reactions and they're both written as reduction, how do I know which one actually is going to get oxidized? Right?
So you just see which one's more negative, so it needs to like have a positive voltage of that.
Good. So they give you, once again, these, I don't know what their cell values are, so I'm just making up numbers. But let's say this one hypothetically was 0.5, and this one, let's say, is 0.7. The biggest thing is if the battery or cell is going to operate on its own, the overall combination has to be positive. But one of these has to flip. So it's a matter of which one can I flip, but then add to still be positive. So in this case, which one would I flip? This one, because if I flip this to negative and I add them, I'd still get a positive voltage. Okay, so that's kind of something to keep in mind is like the voltage should always be positive. Kind of some words that also indicate that is if they call the cell galvanic. Galvanic cells are always spontaneous. They always just happen on their own. The opposite are electrolytic cells. Those are the ones that you have to put energy into.
Do they ever on the FRQ multipliers make it so it won't go on its own, or is it always galvanic?
That's a great question. I don't want to say never, because AP just loves to make it. But I would say generally we are working with galvanic cells, because otherwise it's like, what was the purpose of building this? But there definitely would be some indication if they didn't want it to be spontaneous. Like it would say something that would help you know that.
Like on page 20 when it says number 5, it's this, like it's the same thing. So it says if sufficient voltage is provided.
Oh, there you go. Which one's that?
Number 5, 20.
There's my book here.
It also says within the copper. So you can just like,
But yeah, so there'd be just like pay attention to what's given, because it could go the other way as well. So, okay. So now that we've established established how we know which way the electrons are flowing if it's not told to you, okay? So then you do need to understand, because the process of as it's happening, what's going on at that molecular level. So as this one, so based on our structure here, we're saying that this one is silver and this one is copper, because silver is being oxidized, losing the electrons. So what's gonna happen to this silver electrode as the cell runs?
It's gonna start breaking off from itself and
Very good, so this one's, marker's not working as great as I wanted. This one is going to decrease in mass. Right, that metal, just like when we did the demo of it, the copper wire, I guess I have this backwards, but it got smaller, right? So this one is gonna decrease in mass. What's gonna happen with this one? Good, so there's, I guess we didn't point out, but they're always in solution, right? So the copper that's in the solution will attach to it because of the electrons coming over, right? So the positive come to the negative, and this one increases in mass. Biggest thing to remember is it's never, you can't use electrons for a claim of mass, because electrons are like negligible when it comes to how much they actually weigh, right? The electrons are causing them to change, but you can't use them as the claim of why it's getting lighter or why it's getting
You
heavier.
have to say it attaches, it makes.
Yeah, the ions in the solution are attaching onto it and making it, or vice versa. It's dissolving and silver ions are going into the solution. So, okay, now coming to the salt bridge. What's the point of the salt bridge? Why is it there, Izzy?
to allow positive and negative things to switch to the other side, so it doesn't become one side super positive and one side super negative. So it's not
Perfect,
there.
yeah, so it's all about keeping the neutrality of the cell, right? Keeping it neutral so things can continue to flow. So, how do I know which way are the negatives going and which way are the positives going?
Going the opposite way as the wire.
Yeah, I think of like the continuousness of the negatives, right? So negatives are flowing this way, so the negative ions are gonna keep flowing the other way. Now, something I wanna point out from our last Unit 9 test that I didn't get a chance to clarify before. So sometimes the salt bridge is just a surface, and the ions in here are the things that are traveling across it. Sometimes the salt bridge comes with its own substance. It's like a gel-like salt. So like on our test, it said the salt bridge was a KNO3 solution. So those are the ions you want to emphasize in the salt bridge, are K plus and NO3 minus. So I would show, okay, that the NO3 minuses are flowing this way in the salt bridge, while the K pluses are flowing that way. If you ever need to label a salt bridge, you have to pick, like, show specifically what it is, because you don't want to just say negative, because then it can be deceived of like, are they thinking it's an electron, which electrons are not in the salt bridge. So, okay, any questions that have come to mind about that so far? Okay, so, let me open this up so I don't forget something else with Unit 9. We kind of already talked about the calculation side, so to get an overall E voltage, you just add the two half cells together. Another way we've seen in some other problems with voltage to be aware of, so voltage is additive, it's inverse, I don't know what word is there, but like if you inverse it, it goes to negative, but if I double this reaction, this does not change. Voltage is not an extrinsic property, right? The more you have doesn't make more voltage. It makes the battery last longer, but it doesn't increase cell voltage. So keep that in mind, because that is very different from heat, right? Like delta H, if you double a reaction, delta H will double, but voltage is not that way, so be cautious with that. Let's take a look at, while we're talking about math, and we'll just look at the other reactions that are in this unit, or other equations on your formula sheet that we could come across. And then I'll see if there's anything else in my overview book that we missed. Alright, galvanic cells. What's the connection, and remember the connection between E and delta G, thermodynamic favorability.
So if E is positive, delta G is negative.
Good, so they both tell us the same information. So what Harsh said is that if E is positive, then delta G must be negative. Like, it is impossible to not have this, right? Like, if it's gonna be, or vice versa, right? Like, if this is negative, then this has to be positive. I think there was a problem. I was taking all of your practice tests while I was on the airplane. Because, you know, who doesn't want to just take AP practice tests? But there was a question that was like about this relationship, and you could narrow out two of them really quickly because they were just implausible, right? Like, this relationship would never happen. So, Izzy.
Why is it that they always have to be opposite from each other?
It's that both of them, this, what does it mean if it has a positive voltage?
It means it's being reduced? No.
This is
For overall.
Oh, overall.
So if this overall has a positive voltage, what is that telling me about this cell?
It's, it can happen spontaneously. It's thermodynamically favored.
Which is the same thing that delta G tells us. So, does that make sense? Like, you can't say it's thermodynamically favored for voltage, but not for energy. It's just two different units, pretty much.
Okay.
So, yeah, great question. Any other questions on that? So we do have an equation if you look under the thermodynamics section. There is an equation if you were to have to mathematically calculate it as a reminder, that delta G equals negative NFE. So that is like if you were given one, you can mathematically find the other. One reminder, and hopefully you guys are feeling more confident with your formula sheets, but a reminder that the formula sheet defines all the variables. Right, so if you come across a question and you can tell it's mathematical and your brain's like, I don't know what to do, I would just scroll after I do all my other questions first, right? Skip it, come back later. When you come back to it, scroll through all these variables and be like, oh, this problem talked about current. Oh look, there's an equation for current. But that can help a ton if your brain says, I have no idea what to do. So, Michael, did you have a question?
I was gonna ask, but any math part.
Oh, okay, perfect. But yeah, it's good to remind you. So N is the moles of electrons flowing. So in this case, for this reaction to happen, there's 2 moles of electrons, because copper has to be 2 and you can't like, so then you have 2 silvers. Does that make sense? And then F is a constant, and it's just on there. It's 96 something, something, something. Done. So, any other questions on that equation? The voltage one, just as a side note, like that's not on your equation, right? That overall voltage is just additive. It's pretty much you just flip the one that needs to be oxidized and then add them together. So, but it isn't on your formula sheet for whatever reason. Okay, and then the other equation that deals with it, that once again is kind of, I don't know, it's like a sporadic equation in terms of it shows up some years on the AP test, some years it's never there. Is this one that deals with current. So I is the current measured in amps. This is a little confusing because we have a lowercase q and another thing, but this is like, it's not heat like in MCAT. But this one is charge, and then T is the time. This is really one of those equations, once again, I would just say, like, if you see a question and it deals with current or charge, like, they're gonna give you the pieces of the algebra, and then you just solve for the one that's missing. The biggest thing to recognize is also on your formula sheet, but this unit relationship can make that question or that problem less confusing, is that 1 volt is the same as 1 joule or 1 coulomb. So sometimes that can be helpful because the units sometimes maybe don't match as they should.
also for Q, it should be in coulombs, right? So one of the FRQs that gives you the amount of electrons, so it defines Q.
Yes. Yeah, so Q in this case sense, oh, that marker just died on me. Okay, yeah, so this is also in, yeah. And so yeah, depending on what's given, sometimes you'll use the Faraday's constant for a unit relationship, so. I don't know if that answered your question about that equation, Harsh. I'm trying to think of more examples I've
The
seen.
sum
but-
kinda explained it, so.
Oh, good.
Yeah, it made sense when he explained it. It's interesting, because also the answer said were coulombs of electrons per second.
Uh-huh.
So then you find the electrons and then basically take the amps and it was different than this, like he didn't use this equation.
Oh, okay, but he used the
And-
Faraday's constant one?
Yeah, they used the Faraday's constant.
Is this number 5
It's number
Yeah.
5.
on 2021?
Number
Just
5.
look at it real quick. One thing to keep in mind is that maybe you haven't considered with this idea is that Faraday's constant, similar to like Avogadro's number, can be used stoichiometrically, right? Because it's a
Yeah.
relationship of coulombs per electron. Oh yeah, that's literally what they're doing on part C, right? Is it's just stoichiometry, but using Faraday's constant. So, and then I guess they did use I right here.
Yeah.
They must have given, did they give that to you already? This answer, he doesn't show me what they originally gave you, but.
So let me find, yeah, they give you 5 amps.
Oh, okay.
Just how many seconds you.
And so that you can then translate that into using this relationship of Coulomb per time to. I could try to think of some other ones that we could practice the next 2 days, just to like get familiar with it as a stoichiometric unit, because we didn't really like use it a ton in that sense. So. Okay. These are the equations I can think of that deal with voltage. The only other thing with this topic, and then we'll move on unless other questions come up, is understanding non-standard conditions and how that can influence your cell. So the voltages that are given, like in the textbook or given to you, are always under the standard condition, which honestly temperature and pressure don't matter a ton, like you don't really think about them when we're doing voltage, but concentration does. That standard condition is when both of these are at 1 molar, but if you change their concentrations, I think of it like Le Chatelier, you can drive the force more to product, creating more voltage, or vice versa, you can drive it in reverse, which then decreases voltage. So non-standard cells. We had on our Unit 9 test, there was a question that kind of addressed this, and I've seen a few multiple choice that do as well. So let's say if that's our setup, okay? So let's say so standard is how it's set up, 1 molar, that's what's happening. Our overall voltage is gonna be 0.2, that one's gonna flip to negative. Okay, so let's say hypothetically, we'll call this beaker A and beaker B. Don't say anything out loud, let everyone think for themselves for a minute. But let's say in beaker A and B, I change them to both 5 molar. So what I want to see is that going to increase, decrease, or no change to the voltage? Don't say it out loud, but think for a second. Okay, increase both their concentrations. Is the overall voltage still going to be 0.2, or would it change that? Okay, turn to someone near you. I don't have a table, buddy. You can find somebody near you and share with them what you think. Increase, decrease, or no change. Ready, go. You can make little circles with a variety of things.
So A for
5 times smaller.
So when
Yeah,
it's
but
low to
what is
C
the
gap,
molarity down?
the concentration of C is supposed to go because the metal's increasing more.
That's true.
Okay, ready? Point up for increase, point down for decrease, point sideways for no change. So is it gonna increase, decrease, or no change? Oh, good job, no change. So we have the same voltage. We all got it right, but just to make sure we understand, it's the whole idea of since we changed both of Le Chatelier's idea, right? Like it's not going to drive it in one direction. The battery would last longer, possibly, because you have more anions to attach right there, but it's not gonna make it go up in voltage. Okay, same question, new variables. What if this one I keep at 1, but this one I change to 5? What's gonna happen to my voltage? Think for yourself for a second. Okay, turn to your table buddy and see what they're thinking. Ready, go.
Well, if A is 1 and B is 5, these concentrations are shared, but once they make it so both equals the same concentration. So if it sends the electrons over to C, the concentration of B goes. So if this is more one-thirds of molecule concentration.
Okay, let's see your votes and then we'll talk about it. So increase, decrease, or remain the same. Just whatever you have is quit. We got some ups, we got some downs, we got some seams. Okay, so let's come to this really quick, and here's how my brain thinks through this. Okay, in my setup, we talked about how metal gets changed, right? That this one decreases in mass and this one increases in mass. Let's now talk about the solution, concentration. What's going to happen to the concentration of this solution as the cell runs?
It'll go up.
Why is it going up?
Because, yeah.
The node is dissolving into the solution.
Good. So the concentration, so brackets, FYI, are notation for concentration, right? So if they put something inside brackets, it means molarity. So the concentration of this side is increasing because it's breaking apart in a solution. What about this one over here?
It's decreasing.
Very good. So this concentration is decreasing because, like Ada was pointing out earlier, those anions are attaching to the metal strip and they're not in the solution anymore. The idea of, once again with this, is a cell's going to run until the two concentrations, right, like, are equalized. And so you get, that's the way I think about it is, okay, is having a higher concentration over here going to help the battery in its process? Yes or no? Yeah, because I need those things to attach to the metal. So if this has a higher concentration, it's naturally decreasing. So if I add more to counteract that decrease, it's going to help pull those electrons across faster. Or, yeah, I guess you could say faster. So this one would have a higher voltage compared to the original 0.2.
Is that why like batteries are reversibly chargeless? Because one of the solutions is gonna have a lower mass than the other, so like the last electron sort of goes in exactly.
What was the original thing you asked?
So like batteries have like they have less charge, they're gonna have like lower voltage.
Oh, yeah. Mm-hmm.
Because one of the solutions is like lower concentration, like so B would be a lower concentration then. Because
Yes. Yep. And then what, because over time, this concentration will start going up, this concentration will naturally go down until the
then
battery
you
runs
recharge
out.
it, it reverses.
Yep, yep, and then you reset it. So, okay, questions on non-standard? Obviously, if I flipped it, then we would see a decrease in the voltage, so.
Is there an equation to calculate like the exact voltage that you'd have during a non-standard?
Great question. There is, but you don't have to know how to do it. But one day, if you take more chemistry, there is an equation that does that. So it's called, it actually I think is in your textbook. It's called the Nernst equation, where you can actually plug in, and we kind of looked at it once where you plug in Q versus the original, so like under non-standard conditions.
Yeah.
But what the AP curriculum says is it says that students will not be expected to use the Nernst equation, but they should understand how it's going to be affected, big picture wise. So, good question though. Okay, any other questions about electrochemistry that people have? That's all I can think of. Any other things that come to mind before we move on to the next thing? You check my unit 9, yep, that was the end. Okay, check. I know it's love check boxes. Okay, I'm gonna erase all this, and then we'll talk about IMFs. Okay, so let's talk IMFs. So once again, just a reminder as you're looking over things this final week, that Unit 3 and Unit 8 are weighted heavier than all the other units. So if those aren't ones that you have chosen to go over in a study group, they might be a great one too. IMFs are part of Unit 3, so. Okay, yeah, first.
About how long does it take for you to get your results for your test?
July.
July?
Yeah, it's like, I haven't looked officially, last year was July 10th, I think, somewhere around there. I know, it's so annoying, because you take it and then it's like, well, then you kind of forget about it for a while. And then sometime in the summer you'll be like, oh, my scores. At least that's something as a teacher, that's what happens. Is all of May I'll be stressed about it for you guys. And then I forget. And then I remember. And then it's so exciting to log in and see. Okay, so, I don't even know where to start. Let's see. IMFs. Okay, let's just talk first off. What is the difference between an intermolecular force and an intramolecular force, aka a bond? It's fundamental, but
Intermolecular forces are between the particles, while intra is between the neutral atoms.
very good, right? So intermolecular forces are the forces between. It's the friendship force. If it's ever depicted in a diagram, it's always depicted as a dashed line. Solid lines are used for a true bond where electrons have actually been transferred or they're actually being shared between them.
The sub last time
Yeah.
was telling us that covalent bonds and ionic bonds are actually like the exact same thing. Yeah, he did. We were outside and he was telling us. Yeah, no, we were outside and I was taking it and he was telling us that at some point with the covalent bond, electrons.
Except for like some atoms, like covalent bonds are so strong they're almost atoms.
Oh, yeah.
Yeah, something like that.
Yeah.
That's not what he said.
I'm sorry.
We got there in the end. Okay, so let's talk about the 3 main types of IMFs and then the 4th, also an IMF to consider. So IMFs. So we have London dispersion. Okay. So I think it's important to understand, so you need to be able to identify whether something has that force or not, but then it also can be powerful to understand what causes it to increase in strength, right? Like if I'm comparing 2 things with the same force, why this one has more of that force than the other. And then also what's causing it to happen kind of then puts it all together. So let's start with that of what is, I guess I'll say the cause. What is causing a London dispersion force to happen in a molecule? Go ahead, Harsh.
Electrons in the molecule.
Good, right? It's that temporary dipole is the way I like to think about it. Oh, I don't know, maybe it's still temporary. There we go. Right, we're in an atom. Okay, so here's my original atom. Okay, I'm just gonna say, for simplicity, I'm not gonna draw rings here. Okay, so there's the nucleus, all these are electrons. Okay? Electrons are in constant motion, they don't ever stop. And so, based on laws of probability, there's a chance that all the electrons could be more on one side of the atom than the other. We call this polarizability, this idea of it becoming polar. Now the difference is it's only temporary because there's nothing holding the electrons there. And there's nothing on the other side of the atom, there's nothing pulling them to that spot, it's just, they just all happen to be that way. In one of my college textbooks, I mentioned this before, that they call it the squashiness of the electron cloud. That the electron cloud kind of gets squished to one side for a moment, resulting in a negative side and a positive side. So this was the before, and this is after that happens.
You put them both as positive sides.
Oh, thank you, Izzy. negative and positive side. And so then what happens, so let's say for example, neon does this. Neon experiences only London dispersion force. So what happens is if I force neon to become a liquid, because naturally it's a gas, and gases do not experience INFs. They don't, they just move too much, they're never by each other, they don't have friends, okay? That's that, but how it goes. Okay, but if you force something down to a liquid, the reason why it eventually can become a liquid is because if this is one neon atom, it can then have an experience with another neon atom because negative and positives attract, right? And this dash is that London force between them, okay? Okay, so that's what causes it to happen. So what type of molecules, or how do I identify that something has London?
Well, everything.
Everything, right? Because everything has electrons. I almost wrote everyone. Right? If it has electrons, then it experiences London to some extent. Now, we've seen this over and over and over again of how you can have something that can experience London and it can be quite strong, even though often we consider London to be the weakest of the three forces. So let's see. That's how you identify it, and then maybe if we say comparing. Okay, so if you're comparing London versus a London, right, like sample A has London, sample B has London, how do I know which one is going to have a stronger London, Rachel?
Because whichever one has more electrons.
Very good, yeah. So more electrons, or you could also say more mass, because technically, like if it's heavier, it always has more electrons, right? That's going to equal greater London forces. Any questions about London forces? Okay, let's go to number 2. So dipole to dipole forces. All right, what causes a dipole to happen in between two molecules? Because the molecules themselves are truly polar. So the difference here now is, if it's a single atom, it's only going to experience London. Dipole is now you have to deal with a molecule because now you actually have a permanent shift in it. So I'll pick a simple one, let's pick HF. Okay, so if I have the HF molecule, okay, so it's two atoms, they're bonded together. It's going to look similar to this, but now this time the difference is, why are the electrons going over here? More electronegativity, right? Higher electronegativity pulls the electrons towards itself, and so that's why this is what we call a permanent dipole. This is temporary, they can easily go back. This one's never going to go the other way, ever, right? They're stuck in that position. And so then the dipole is between, man, all my markers struggling. Alright, so then when it comes in contact with another thing, right, this is the dipole force. Once again, it's all about positives and negatives. Yeah.
So when you're figuring out something that has like a strong dipole force, you always like write it out to see what a positive and negatives are.
It kind of depends on what the question is, to be honest. If you have to, so let's go with this, and this might answer what you're asking me. So how do I identify if something has dipole forces? A polar molecule. And to me, in order to determine if something is polar, you have to have a Lewis structure. Or it's like, I guess, something simple like this. But you have to know what it looks like in 3D. Because the shape of something is what is causing it to be polar, right? As you get bigger structures versus just like a 2-1.
So when something has dipole forces on the test, will it show you, well, if it has the possibility of having a dipole, will it show you on the test the structure of it? Or will it be some cases will it ask you what IMFs it has and won't show you a structure for it?
From my experience, the second thing you said is more likely. That more likely are they to give you, let's say hypothetically, they could say, they would just give you formulas and they'd say this, right? And then it's up to you to determine what forces does it have based on drawing out their shapes. So, did that answer your question, Izzy? Yeah, great question. Did that answer what you were kind of asking too, Aiden? So yeah, so if they just give you this, draw out their shape to determine whether it's polar or not.
Is CH2F2 polar?
It is.
Way more polar.
Yeah, because the tetrahedral doesn't actually set them
And the CH4 has.
straight across from each other. So that would definitely be something if you are struggling with IMFs, check and see if you're struggling with shapes. Because if you can't do shapes, you can't do IMFs correctly. And then that might be something you need to review a little bit more. So, okay, questions on that? Okay, comparing. So if I'm comparing, let's start with this comparison. So if I'm comparing dipole versus a dipole, any ideas of how I know which one's going to be stronger?
Whichever one's more polar.
Yeah, more polarity, which would be a greater difference in electronegativity, right? If they're farther away from each other, it's gonna be a bigger pole. So more polarity equals more dipole forces. Okay, what about comparing London versus dipole?
Dipole's usually stronger, but like there's a bunch of questions for like one is a higher boiling point, but it has only one dispersion. They would just say that it's more like
Yeah, and I'm glad you noticed that trend, Harsh, because they love to do the exception, but they always give you data. So I would say with this, if you're comparing something that has London to something else that has dipole, and London, of course, because Röntgen, everything has London, then I would say look at the data. Because the data will tell you what type of force it has. And they'll always give you data. Because otherwise, there's that weird overlap of it. The way I think about it, like if you want to look at this, like when you look at the strengths of forces, okay, so here's like a timeline of strengths. It's like London's fit from like here to here, right? But dipole fits from like here to here. And so even though, yes, but there's a big overlap region, right, where, yeah, like if you have a London that's up here, but a dipole over here, it's gonna overpower it. So look at the data, and we can review what type of data they'll give to you in a second to look over that.
And then hydrogen bonding would be always.
Yeah, very good, yeah, hydrogen bonding's like just shifted somewhere. Right there. And then in comparison, if we were to add ionic bonds to this chart and an actual covalent bond, they're like out the wall. Like they're so much stronger than these types of forces. So,
Will anything with hydrogen bonding be like weaker than something with just dipole or under dispersion?
let me clarify, so are you saying, is hydrogen bonding always gonna be, yes. Yeah, so there is no overlap region where something with London could be stronger than something with hydrogen.
You gotta recognize when it does actually have hydrogen bonding.
Yes, yeah, good question. Okay, any other questions on dipole? Okay, let's go to hydrogen bonding. Okay, so hydrogen bonding, what causes it, what's going on there?
It can only happen with nitrogen oxygen fluid, right?
Good, okay, so this is our permanent dipole. Okay, so let's add over here, I'm gonna erase this. So the way we identify it, as Aiden said, is it's a molecule that has N, O, or F, and the H has to be directly bonded to it.
It can't be next to it.
Yeah. so that's how you identify it, is if you see a molecule that has N, O, or F, and those are directly bonded to an H, then that substance can experience hydrogen bonding. Now, what is it? What's going on with hydrogen bonding in terms of our like other comparisons?
Is this really cold?
Yeah, the way I like to think of it is it's an extreme dipole. It's the same thing, but it's more of an extreme force because of the combination of one of those and the H.
Isn't HF also hydrogen?
Oh, yeah, it is. Picked a bad example. Should I change that? Is that
Change to like CO.
I didn't even notice that harsh. I just picked a random example. Okay, so let's say we pick HF. So it really looks almost the same, right? The electrons are being pulled away. What's the general trend for electronegativity, as a reminder, remember? Very good, right? Bottom left, upper right. Noble gases, though, don't have electronegativities, right? Because they don't bond. So the difference here is the electrons are still being pulled in this direction, but why does it make it so much stronger?
Because N, O, and F are the like atoms with the highest electronegativity, and since they're so electronegative, they just steal hydrogen's electrons, right?
Perfect, so one is these pull with more strength than all the rest, right? Then who are they pulling away from?
The hydrogen.
And what happened, how many electrons does hydrogen have?
It's one.
One. So when you pull the electron away, you're exposing an even more, it's like my emphasis positive, an even more positive sign. So it's the same idea, it's positive, negative, negative, positive, right? They feel attracted, but this plus and this minus are like amplified, right? That force is a lot stronger between them. Right, so this would represent the hydrogen bond. Because this is negative and that's our positive. So, okay. Questions on identifying hydrogen bond? Alright, so we talked about that, we talked about how to identify it. We kind of already talked about comparing it, because hydrogen bond is always the highest. And honestly, I've never seen a question where you have to compare one hydrogen bond to another. Because that feels
It's redundant. Well, there are kind of some multiple choice ones I've seen already in the multiple, where it's like one has some that could hydrogen bond, but then there's more.
oh, that's
And
true.
another
Sites of
molecule.
hydrogen bonding, they they do really big molecules, and it's like, oh, this one can hydrogen bond at like 3 places,
Yeah.
versus this one that can hydrogen bond at one site. Yeah, that's a good example, Xander.
So if there's only one, like, if there's two molecules and there's only one hydrogen bonding it, like, would it, the one with, like, if it was like oxygen, one with hydrogen and chlorine, one with oxygen, hydrogen, would chlorine be the stronger one?
Yeah, like if we were to compare, it's not a real molecule, but like hypothetically, if HO were a molecule, I would say HF probably has more forces than HO does, so, yeah, good connection. Anyway.
So hydrogen bonding is like between two molecules, right? Like if you just had one molecule with like hydrogen and chlorine, you wouldn't say that that's like hydrogen bonded.
Very
That
good.
would just be like a covalent bond, right?
Yes. Yeah, so I've seen a few questions, I don't know if there have any come on in yours, but like where it gives you a picture and it's like identify where the hydrogen bond is, and it's always the between. Yeah, even though it's called a bond, it's still just an IMF. So yeah, good connection. Any other questions on IMFs? Okay, let's talk about a fourth one that we have seen, just to be familiar with, that it's kind of a special situation, but just to keep in mind, of the ion to dipole force.
Is that stronger than hydrogen?
No, it's kind of its own category. Michael.
Is that like when water like surrounds an ion in a solution?
Perfect. So I'm getting kind of low here. Can people see this low on the board? So this is where that you've seen lots of pictures of this and drawn them yourself of in solution. So ions have to be in solution. So this is the connection of an ion being attached with something that is dipole. Keep in mind, like the names like tell you what two things are connecting, right? So an ion to dipole is the whole thing of in water. My sub just draw with my markers a whole bunch of
You didn't really use it.
he just like drew a bunch. Okay, so in water, if I have a positive ion, because water is polar, that's in a sense what causes it to dissolve. And so then how does water interact with that ion?
The negative side of it connects to
Very good. So if I draw these as Mickey Mouses, and that's often how we draw the water, it would always attach in this orientation, while the negative one, right, would be attached on the positive side. That right here, this force, which I guess here's the weird part, they don't typically draw dashed lines, they just show it connecting, but that little force right there is the ion to dipole force. What was that, Harsh? Oh yeah, we can talk about twin beta networks too. I forgot about those. But that's, yeah, the ion dipole force. So the way you identify it is it has to be an ion in solution, right? Pretty much, I guess, has to be ionic because ionics break up. So this is when you have something ionic in, I'd say it's always water. It doesn't technically have to be, but it normally is. And I guess I'll say in a polar solution. As long as it's polar, then it can do the same thing. But, and once again, can't really do comparing because it's kind of its own category of things. So,
So could like hydrochloric acid technically be a polar solution?
yeah,
Okay.
yeah, yep. It'd be, and most of the time it's already aqueous, so it's already in water too. So yeah, no, but there's certain things that don't dissolve well in water, but they can dissolve, like in acid you can dissolve them. So. Okay. Any questions before I erase what we have so far? Yeah.
So what kind of information would they give you to tell you that London dispersion is stronger than the
Perfect. That's where I was going next. I was just going to clean this off because I ran out of space. Okay, so let's talk about data in relation to IMFs of all the different ways, like if it's a comparing thing, or whatever other question they're asking. So this is something that you need to be really aware of, in that with the data that relates to IMFs, you've got to make sure you I don't know how to say it, like the word hints in the question, that if you have a question and it deals with any of these things, boiling point, vapor pressure, melting point,
Let's say it's a solid.
oh yeah, state of the matter. Like solid, liquid, or gas. Solubility. Similar with solubility, they can talk about if it's miscible. Oh shoot, I don't know if miscible is has a C in there. Or immiscible. We can go through these in details, but when you read a question, those are all I can think of, but I'll let you know something else anyway. And if it deals with one of these things, your brain needs to recognize this question is rooted in IMFs. Because a lot of the questions aren't going to straight up say, like, what are the IMFs? But in a sense, to answer the question, you have to think about IMFs. So it's kind of, you got to catch those words of anything that deals, and really, it's kind of all about phases, right? Like, it's not a chemical reaction, right? These are physical changes. I guess that's kind of the category we could group them as, right? Like, if it's a physical change that's going on, right? So like boiling it, evaporating it, melting it, dissolving it isn't a chemical change. It's just a physical change, and all physical changes are results of a change in IMFs, right? Because ice, to get, water's a bad example, but solid, right? Liquid, yes, right? It's all about just how close those molecules are. So let's go through what this information would tell me about the IMFs. So if, don't say it out loud, but think in your head, if it gives me information about boiling points, the thing with the highest boiling point, what is that telling me about that substance's IMFs in compared to the other one. Don't say it aloud. It's either up or down, by the way. Right, so if something has high boiling point, what does that mean about its IMFs? Point up or down? You should have your answer. Very good. Yep, so high boiling point means higher IMFs, because IMFs are what hold them together. And so if they hold tightly, it's going to take more heat to break them apart. So for example, coming back to this, if this substance, or this comparison, there you go. Right, so if I have a substance A that has London forces, and substance B has London and dipole, but the data shows that this one has a higher boiling point, then it's due to the fact that its London are that much stronger than the dipole. Does that help me give you that vision a little bit?
It's that overlap.
Yep, it's that overlap region. And the Y, like if it's an FRQ, like this is the Y. It's probably a pretty big molecule with a lot of electrons. So, okay, vapor pressure. Don't say it out loud, the thing in your head. If something has high vapor pressure, what does that tell me about its IMFs? Very good, it's inversely proportionate. Because vapor pressure, right, is in a closed system. There's liquid in there. Vapor pressure is the pressure that's going on above the liquid based on how much gas or vapor is in there. And so if something has weak IMFs, then they're more prone to just become a gas already. So, questions on that one? Melting point, so if something has a high melting point, what does that tell me about its IMF? Show me your vote. Very good, yeah, very similar to boiling point, high IMFs. With states of matter, if something exists as a solid at room temperature, while another thing exists as a gas at room temperature, what can you claim about their IMFs?
The one that's a solid has higher
Yeah.
Fs than that's a gas or liquid.
Yep. Yeah, it just, right, obviously the stronger ones are gonna hold tighter. Let's talk about this one real quick. I had a thought come to mind, and then we'll come down to solubility. So it kind of applies honestly to everything when it comes to IMFs, because IMFs are all about positive and negative things. So let's review really quick Coulomb's law, because it has a big implication here, but it's kind of a theme throughout all of chemistry that's important to recognize. Anyone remember in general what Coulomb's law tells us?
It's like distance influences like how attractive things two things are, and also how positive or negative it is.
Good. So Coulomb's law in simplicity is all about positive and negative things are attractive at all times in every case. But that attractive force is influenced by two factors. I think Vector from Despicable Me. What does he say? Right, so it's all about direction and magnitude. You have to the direction does make sense, but with it, it's all about how close those two things can get. So the closer they get, the stronger the force. In terms of atoms, distance really means size. Big molecules, like a big positive and a big negative, have less Coulombic force than a small positive and a small negative, because the distance, right, affects it. And then the other one is magnitude. So it's affected by distance and magnitude, which is how positive and how negative. So for example, like a +2 and a minus, right, this would have more magnitude than that one because of the +2, and so that Coulombic force would be stronger. So when it comes to melting, this is what you should think of when you think about ionic solids. Because ionic solids don't have IMFs. So if we wanted to add that on here, so melting point for ionics, right? It is all about Coulombic forces. That the higher the Coulombic forces, right, the higher the melting point is going to be. And then solubility is dissolving things in other things or mixing them together. Could be a solid in a liquid. Miscible is typically used for liquid in a liquid if they mix. What is the connection we're looking for with IMS if we want to know if two things are going to dissolve or not dissolve? Lily?
If it's like easily soluble, then the IMS are weaker because it has a lesser hold.
Close. It's not about it being weaker, but you're on the right track of like that connection. It's about similarity. So we want similar forces. And forces will dissolve together. Sorry, I'm making up that sentence in my head. It sounds weird, but. So if something has dipole forces, it will mix well with things that also have dipole forces. But if you have something that has dipole forces and it's mixing with something with just London forces, like oil and water, then they don't really mix. Alright, so often it's really nonpolar versus polar is really how you can think about it. You can get into more detail with like hydrogen bonding, but most questions, if you can narrow it down to this, that nonpolar will dissolve nonpolar, polar will dissolve polar, but they don't dissolve each other well. And it's not because they're repelling, it's about interacting, right? That polar are going to interact with other polar things. The non-polar things, right, will just, or polar things don't really interact with non-polar ones. Right?
So the reason oil and water doesn't mix is because of IMF, not density? That's what I've always heard, is it's density.
Nope, it's really IMFs. Yeah. Now, density plays the role in terms of, like the oil's on top and the water's on the bottom. But if you get two things that have similar IMFs, the difference would be like if you shake it up, right? If they have the same IMFs, like you would eventually get some separation out, but it's not going to be very quick because then it's just the density pulling them apart when they're actually somewhat attracted to each other. So yeah, great connection. Okay, any other thoughts?
Can you also talk about like is it chromatography, the paper thing?
Oh yeah, let's connect that over. Okay, so with IMFs, chromatography is a way in which you can identify, so it's a lab technique to identify IMFs. Let's review chromatography really quick. So chromatography is you have some strip of paper. Right, this is the one we did with the candies.
Oh yeah.
Remember that one? Yeah, the different colors. So typically it's colored, hence the word chrome. But technically it doesn't always have to be colored. You can do them with under UV light. So you can't always see the differences. But anyways, so chromatography paper, basic setup is you have your starting line. I'm gonna think of it like a race. Right? You dot your sample here. And you can do like multiple if you want, depending on the paper. Then you put that into a flask. Alright, so I'm gonna make this picture really big now. Oh, that was a lovely flask. Oh dear, okay. Okay, so we put it in the flask. Oh wait, it has to be at the bottom though, what am I doing? This paper's thrown off. Okay,
That
anyways.
paper's really, really good.
Is
Let's just make it
paper
easier.
also see-through? Because it has a line through it.
Okay,
Nope, other one. There we go.
that looks better. Okay, so we put it in a solution. You don't want the line to go below the solution because we want the solution to climb up, right? As the solution climbs, what you see happen is the colors or the spots start to move. If this is a pure sample, what am I going to see for sure when it starts to move? One color. Good idea. Right? If it's a pure sample, you're only going to have one color, one dot, and the dot's just going to move. If it's a mixture, what am I going to see? You should see different spots, right? So like this one might have this, but let's say if this one's a mixture, it might have like this, and then like something up higher, right? Spread out. Okay, so now the question is, so one, it can be used to identify mixtures, right? If you don't know if something's a mixture, but then it can also help you understand the components of it. The catch with chromatography is you just have to label pretty much this in terms of what is the paper and what is the solution. They will tell you in some way or form like what they're using. They may not tell you if it's polar or not, but they'll tell you the substance. Like for example, they might say, okay, we are using a sodium chloride solution. And then the paper, they sometimes will say, sometimes they won't, but then they could tell you that the paper is like a non-polar chromatography paper, right? But there should be a difference between the two somehow. But it's not always set, right? So in this case, this one is polar. This one is non-polar, but don't memorize thinking it's always that way. It could be reversed, right? The paper could be polar, and the solution could be non-polar. So pay close attention to what the problem gives you. But then connecting to this, so if a dot travels really far up the paper with the example I've drawn, what does that tell me about it, Izzy?
I mean, it's polar because it travels with the polar.
There you
more
go.
than the
Polar hangs out with polar, right? And the polar is moving up the paper with the water, and the non-polar things stick to the non-polar paper, or they don't get attracted as much to the water. So, and that's all the questions I've seen are always about like the polarity of them. So, good connection with chromatography. Any other thoughts on hydrogen bond? Not hydrogen bonding, IMFs in general. Oh, let's talk. We forgot about. You mentioned it. What did you say? Covalent networks. So we have. Okay, I'm gonna erase this. Okay, so our bonds we talked about so far. So we talked about London forces, dipole-dipole, and hydrogen bonding, which all fall in the category of an IMF. Okay, some molecules, oh, side note. Let me keep going actually, I'll build my side note. So, some molecules don't experience IMFs because all their molecules are actually just truly bonded to one another, such as ionic bonds and metallic bonds and covalent networks. Okay, so IMFs only happen with covalent molecules. Like those are the only molecules they happen with. But some covalents do a network, and it doesn't count as an IMF, and because it's the strength between it's truly bonded, right? Same thing, ionic bonds you would never say have London forces. They just do ionic bonding. Same thing with metallic bonds, right? They just do metallic bonding. So covalent networks are the case where you have a covalent molecule that is truly bonded in a giant lattice. Most covalent molecules can be isolated to a small Lewis structure, as we've drawn many, right? Even this one, which is a little bit bigger, right, it still can be isolated down to a single molecule. But some covalents actually create a giant network of actual bonds. And we used diamond and graphite as an example when we talked about this in class. I don't even know how to draw it on the board. But the idea is it's literally like connected. So like in diamond, it's pure carbon, right? So it's carbon, 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 carbon. But now you gotta think in 3D space, right? Of it continuing this pattern of carbon, carbon, carbon. Obviously it's not flat because you got a bunch of tetrahedrals, but it's all bonded. It's not like hydrogen bonding where I can isolate it down to just a molecule. So, does that make sense? Remember what a covalent network is? What else do you want to know about covalent networks? Oh yeah, so the catch with covalent networks, and I don't really love this catch, of like, how do I know if something does it? You just kind of have to memorize them. That's the best I've come up with. Because there's no way to like look at it, because like the formula for diamond is just C, and then sometimes they write diamond next to it. Because if it was graphite, then it's C graphite.
If it was just carbon.
Yeah, but, so you kind of just have to memorize what they are. There, I guess, is the pattern of pure carbons following the family, because the things that can bond in 4 ways like to make these networks. So if you scroll down, right below carbon, we come to silicon. So silicon as a pure substance also does a network. And then the one that you came across, was it multiple choice or FRQ? But I know you just saw it was
Silicon dioxide.
SiO2 is also
Oh, yeah.
a way that networks.
We were talking about that.
Yeah, he left me a note about that I was looking over this morning, but that's the best I can think of is you just kind of have to memorize. So if you come across it, I'll let you know on Wednesday if I can think of any others that are a network that you should just know. But otherwise, I have seen questions where they just show you a picture, and so you should be able to identify from a picture like, oh, this is not IMFs, it is a network. But if they just give you a formula, just memorize these 4 for now. So, any questions on that? Or IMFs in general? I know that was a lot, but that was hopefully good because IMFs are a big thing. Okay, let's talk rate law. Okay, so do you guys want to stand up real quick? This is gonna be a quick stand. Quick stand. Got 15 more minutes. Okay. What are we talking about? Rate laws, thank you.
Also,
my
I have a question about, KA.
Oh, okay. In general or
About like,
just?
about how like H plus and A minus over H A.
Uh-huh.
What the actual H plus and A minus is.
Okay. We can talk about that. I don't know if we'll have time today, but write it down and we can definitely address it, so. Rate laws, that's good. Okay, so a rate law in general is a mathematical expression that helps you see how the different reactants influence the speed. Okay, so it's some sort of mathematical expression. It always has the same form. All rate laws are rate equals, you always have lowercase k, that's the rate constant, and then only reactants. Sometimes people always mix up rate laws and equilibrium. But rate laws are only reactants, so let's say hypothetically we have A and B. Right, so let's say, I'll just give you my equations. So if A and B are making AB, right? Then your rate law is gonna be in terms of how is A influencing it, how is B influencing it, and they're to some power. So to the power of n and to the power of m, right? Where n and m are what we call the rate orders. Generally, the rate orders are 1, 0, 1, or 2. They can exist past that, but you'll never have to find them. But don't be surprised if in a problem they tell you, like, oh, the order is, it's 3rd order, or I've seen them write like 0.5 order. Like they might give you a weird rate law, but you only have to find these 3, okay?
Are these in equilibrium reactions or just like reactions that only go?
Just any reaction. So equilibriums can have them if you're measuring the forward reaction, but honestly it's just for all reactions, measuring how quickly do the reactants go to product. So, good question. Alright, so keep in mind that these are just reactants. Okay, as we're looking at this, so K is the rate constant. It's not a constant all the time number for all reactions, but each reaction has its own constant that doesn't change. Unless, what factor can change K? Temperature, yeah. So it is temperature dependent. Or in a sense, it's the thing in this that that's showing you how temperature influences it. Because as we know, generally speaking, if you heat up a reaction, it's going to go faster. And so that's what K would change to show that. The units for rate are always in molarity per second. How quickly is the molarity changing per second? Michael?
How do you find K?
Great question. So it depends on what method they're giving you. So let's go through, there's three different ways to get this. And I'm gonna just, whatever the problem gives you. So the first method that you can use to determine a rate law is from, I guess that's a weird, so they're all from experimental data. But in this one, they'll actually show you the experimental data. I'm going to go through the options and then we'll go into each one in detail. So 1 is through experimental data, 2 is through mechanisms, and then 3 is through graphing the data. Am I missing one? No, that should be it. I just think there's 3. Okay.
Maybe half of sometimes.
Yeah, and that kind of fits into, kind of like overlaps with the graphing idea and the experimental data. So with experimental data, this is the one where they'll give you a big chart. So let's say with R's A and B. I'm making things up here, so bear with me. And they'll tell you like initial amounts. I don't know why I did that. That's okay. So here's like your initial of A, initial of B. And then they'll have the rate here at the end. Alright, so it's normally like a big table. So, sorry, this one's hard for me to just think of numbers off the top of my head. But this, once again, the initials like what you're controlling as a scientist. So let's say like I did on that 1 molar, and then this one I changed to 2 molar. Is this ringing a bell to people? So then what you're looking for is I changed this, how did it influence the rate? So these aren't really good rate numbers, but just pretend with me. Let's say on this first trial, the data said that the rate was 4.
Because sometimes they're not,
Say that again.
sometimes they're like not perfectly doubled or.
That's true too, right? And then this one was also still 4. Let me draw some. Say this one. Hopefully that worked. Okay, so what we're looking at is the cause and effect, right? Where, okay, from trial 1 to trial 2, I doubled B, but the rate stayed the same, which tells me B is to the order of 0, because it had no influence on the reaction. It didn't make it go faster when I changed it. But in comparison, if I compare, so this one now, because keep in mind you want to keep something constant while the others are changing. So from this one, A doubled, while B stayed the same. Since the rate doubled, that means A is to the order of 1.
Let's say quadrupled though.
So then, yeah, so if
If it multiplies by
it's
8,
squaring, so this would be 16, then it would be second order. Because think of it, this is going to be a power, so it's to the squared.
Oh.
Or in a case like, if this cubed, then it would 9 double. So,
Shouldn't number 3 be the same as number 4 there? Just for the rate.
oh yes, yes. Because this one we know is 0 order, but that one we now know is second order. Yes. Okay, that ring a bell of how to find it? So that's how, using this data table, you can find N and M. So then, to answer your question, Michael, so then to get to K, is you then can pick any trial, plug it in, because you have the rate, you have A and B, you now have N and M, and you just solve for K. And any 4 trials should give you the same K value. So, does that make sense? So like with our numbers here, I would say, all right, well the rate is 4, I don't know what K is, A is order, first order, I can't remember.
Second order now.
It's now second order, and then B is to the zero order, and then solve for K. They do always, anytime you have to find K on an FRQ, I've always seen it where there is a point for the unit. Because the units never stay the same, you have to mathematically figure it out.
So for that one, would you do one for the second?
So this is molarity, this is molarity, this is molarity per second. So when you square the number, it also squares the unit, right? So this one's going to be,
1 squared.
now this does just like go away,
Yeah.
right? So we're gonna have unit-wise molarity squared, but then it would get divided over. Does that make sense? So we have molarity squared, if I'm just tracking units here. So we have molarity squared and that. So then when I divide by molarity squared to get K by itself, this M would cancel out with one of the M's.
So it's the S over N.
So it's two ways of writing it. I like using the inverse, which means they're on the bottom. But typically it's meaning you have an M on the bottom and an S on the bottom left over. So that's a good one to practice if you forgot kind of how to do just the mathematical part of it. So, any other questions on the data side of a rate law? Okay, let's come over to the graphing one and then we'll end with mechanisms. So graphs of data or charts that can be turned into graphs are another way you can identify a rate law. More particularly, it mostly identifies the order of if it's first order, zero order, or second order. So your data table would look something like this, which is this situation. So it'd be versus time, and then you'd have concentration of A, 1 over concentration, oh I should put them in order that they typically come to you. You have natural log of A, and then 1 over A. Okay, this is ln, by the way. So this would be the data that they give you. And you're going to recall, what are we looking for with this data? Which one is linear? Only one of them will be, to identify a linear trend, it should have constant change throughout. And don't think like timesing by 2 or dividing by 2, right? It's like adding on 0.75, right? Or adding on 1 each time. If this line ends up being linear, then that tells me it is second order. If this line is linear, then it tells me it's first order. And then if this line is linear, it tells me it's 0. And you can see it two ways. Sometimes they're nice and they give you a graph. Same thing though, you're just looking at the units for the graph, right? So like in our case, what did we figure out A was? Second order? So RA would show that the 1 over A graph versus time is linear. While the other graphs, either like concentration of A versus time, or the natural log of A versus time. Right, so only one will be linear in the end. So, yeah, you're good. Okay, questions on that?
Do I use the first two equations and the kinetic section? Because that was in one of the videos.
It's another one of those equations that like,
It's every once in a while.
yeah, it doesn't show up a ton. They're really just, if you understand like an equation for a line, that's what those equations are. Is there X and Y axes? Like, where's that here? So like, K is always the slope of your line, so we think of it like that. And then they're just saying like, you can pick any point, 2 points on the graph with the slope or the time, so. But yeah, I never really do focus on them too much because they never, I don't remember the last time they popped up that were actually like needed. I don't know if it's one of those things where they're like putting them on here to make you think about this, but in terms of actually using them, I haven't seen it in a long time. So that's what they're there for if you were to come across something. But any other questions on the graphing? Okay, finally, mechanisms are another way you can get a rate law. Where a mechanism are the steps of the collisions that are happening for it to happen. So this is the overall reaction, but hypothetically, scientists through data could have figured out that in order for this to happen, I don't know how to make a mechanism here. Let's say A reacts with C to make AC, and then AC reacts with B to make AB. Yeah, okay. That's a good one. I'm proud of myself. Okay, so this is the idea of a mechanism where you have various steps. The overall represents what it's turning into. So why do some of the things disappear? What can we label them as? So what's an intermediate in this reaction?
That's all.
Good. It gets made and then it gets used, right? So that's why it doesn't show up in the overall. What is C in this case?
Catalyst.
No, it's not, see, it's not that.
I guess I should have put that there. Now, what is C? It's catalyst, good, right? Because you start with it, you end with it, so the overall is the same. So yeah, being able to identify intermediates versus catalysts are important. What does a catalyst do to a reaction? It lowers the activation energy, and so it speeds it up, right? That's how they work. Okay, so with a mechanism, the way you get to here is by looking at the rate determining step, or AKA the slow step. So they will tell you which one is the slow step, because you can't determine that by just looking at it. There's two ways to approach it. So if the first step is slow, yep, then the step is the answer, right? Where it'd be, all right, our rate law is, sorry, this mechanism does not match our data from the other two, but this would be rate equals K.
C wouldn't be there. No.
I've seen it both ways. They're okay if you want to throw in the catalyst, but once again, because it's not an actual reactant, I would take it out. Once again, if hypothetically there was a 2 here in this step, how would that change here? Then it becomes second order. So when you're going steps, the order is the coefficient. But with an overall, you can't do that.
And then if it has a subscript, it just goes into it.
Yeah. So there's like BR2, it just if the slow step is second, what's the difference? You have to substitute out the intermediate, because intermediates aren't allowed to be in a rate law. And so in this case, our original rate would be, the rate would equal K ACB, but AC is an intermediate, so I need to substitute it out. Whenever the slow step is second, this first one is at an equilibrium, which plays a big role into it. And so I can come up here and say, well, AC equals A and C together, and so that's what would get substituted in, is A, C, B is my rate law, because this equals those. But hopefully that rings a bell, or reminds you of some things, but if you want more examples of mechanisms, we can leave them to you. Yeah?
So why do we have to get rid of the C? Because it's still a catalyst.
I don't know if I picked the best example, that's why it's like this catalyst is kind of messing us up. Yeah. So I would leave it in there in this case because it did play a critical role in the making of the AC, but generally most of the time you work with a mechanism, there won't be a catalyst when you're having to do the substitution idea. But yeah, great observation. Annika.
If you're dealing with a mechanism and there was like 4 steps, and
Yeah.
so like the third one was the slow one, would you treat it just like you did the second one? Like you did? with-
Yes, so whenever the slow step is not first, some amount of substitution is probably going to be necessary.
Is it like more complicated the more steps there are though?
It can be, yeah, because you could have to possibly do like a double substitution just to get rid of all those intermediates, so. But, any last questions on rate loss? Okay, I will make sure we throw these into the next Wednesday and Friday, we'll talk about those at some point together as a class too. So, one quick question before you go, and if you don't know, but like, you maybe like give me like a rating with your thumb. If I were to do just a final overall whatever questions you guys have on Saturday this week, would you come? Yes? No? Maybe. And maybe on Wednesday I'll do like a survey of like a time of like what time it is for people.
This time on Saturday,
The hard part is, because so our classes this week are Wednesday, Friday, right? Wednesday's a Wednesday, so there's no sky time. And then Friday there's an assembly.